Hi everybody, welcome back to Dave's Math channel. I haven't made a video on this channel in a while. Thought it's about time I made another one. I'm on vacation now. You can probably tell the background's different than usual. I'm in my hotel in Copenhagen in Denmark, and it's my second day on the trip. I'll be here for another week or so. But anyway, today I'm going to talk about a very important unsolved problem in math called the ABC conjecture. And I guess first I have to tell you what it says. So here's the ABC conjecture. So we have we're given three positive integers, A, B, and C. They're relatively prime, pairwise relatively prime. Actually, it's enough for any two of them to be relatively prime. And also A plus B equals C. And then there's a thing called the radical of n, rad n. It's written as rad n. That's just the product of all the distinct prime divisors of n. So what the ABC conjecture says is that for every positive number epsilon, there's only finitely many triples A, B, C. We call these ABC triples, such that C is greater than the radical rad of ABC, the product ABC, all raised to the power 1 plus epsilon. And I think I should also give you a definition here. This number 1 plus epsilon is also known as the quality of the ABC triple. We call it Q of ABC. It's just the maximum value of well, it's just the radical of ABC divided by C. It's actually the logarithm. So you take notice that the 1 plus epsilon is the exponent of radical ABC. So if you take the natural logarithm, or any logarithm, doesn't have to be a natural logarithm, divided by the logarithm of C to the same base, you get the thing 1 plus epsilon, which we're now calling the quality QABC of the ABC triple. So another way to state the ABC conjecture is just that for every triple of integers A, B, and C satisfying the properties given above, the quality of that triple QABC is always greater than 1 plus epsilon. If the quality is greater than 1 plus epsilon for any given positive number epsilon, no matter how small, that means there's only finitely many. There's only finitely many triples satisfying the conditions of the ABC conjecture with quality greater than 1 plus epsilon. That's just another way to say it. And the guys who came up with this conjecture, this is a pretty recently formulated conjecture. There were two mathematicians who came up with this conjecture in 1985. They were Joseph Cesterle. He's the guy on the left. I guess he was a student at the time, and then David Masser, shown on the right. So they came up with this conjecture in 1985. And so far, nobody's been able to prove it yet. That's why it's still a conjecture. Um, but it has a lot of important consequences. Here's a list of, I guess, eight important consequences. There's a lot of other ones. I'll just read these off. So a few of these have already been proven. One is Roth's theorem. So there's an important result. This was proven in 1955. This is an important result in Diophantine equations. Analysis. It's a result in how well the algebraic numbers can be approximated by rational numbers, irrational algebraic numbers. It turns out that irrational algebraic numbers can't be approximated very well by rational numbers. And Roth's theorem, I guess there was a mathematician named Roth who proved this in 1955. And the ABC conjecture would be one way to prove this theorem. And then there's also something called the Mordell conjecture. This has actually been proven. This is another result that's been proven. It was proven in 1985. I guess the same year as the ABC conjecture was formulated, but it wasn't proven using the ABC conjecture. But anyway, that's another important mathematical result. And then there's also Voida's conjecture in dimension 1. Um, and I believe this is a consequence of the Mordell's conjecture. This is, I guess, also known. And then there's a Lang-Woods conjecture for a finite number of counterexamples, that would also follow. And then there's also, it would also follow that there's infinitely many non-Weifrich primes in every base. I don't want to get into what those are. And then there's also the weak form of the Marshall-Hall conjecture on the separation of squares and cubes. It turns out that I think the Marshall-Hall conjecture, I don't know what it specifically what it says, but for every integer n, there's I think there's only a finite number of perfect squares and perfect cubes that are separated by n. I know there's only one when n equals 1. 8 and 9. This was just recently proven. It turns out that 8 and 9 are the only two powers that are separated by 1. Kind of an interesting result. And I guess there's similar results for other small separations. So squares and cubes separated by small numbers are rare. That's a consequence of the ABC conjecture, or would be. And then it would also provide a simpler, much simpler proof of Fermat's last theorem. I think you guys know that Andrew Wiles proved Fermat's last theorem in 1995, but his proof is extremely complicated. It's a 129-page proof involving some very complicated math I don't even understand, algebraic geometry. And finally, another consequence would be the Fermat-Catalan conjecture, which is a generalization of Fermat's last theorem. So as you can see, the ABC conjecture would lead to a lot of other important mathematical results if we could prove it, but so far nobody's been able to. But now I just want to talk about some numerical results concerning the ABC conjecture. So mathematicians, especially with computers, it's been pretty easy to come up with a big list of ABC triples having given qualities. And even though the ABC conjecture says there's only finitely many of any quality greater than 1, we still know quite a few. And this table just lists how many we know for given limits. This is on the left. The left column is given the maximum value of C, and then the right columns just tell you how many known ABC triples there are with qualities given, quality bounds given on the top right. So as you can see, there's only 160 known ABC triples up to with C up to 10 to the 18th and quality up to 1.6. Still quite a few. But then as the quality goes down, the numbers increase pretty rapidly. And already for Q equals 1.05, there's something like 2 million known ABC triples with C up to 10 to the 18th. And the ABC conjecture says this number should be finite. So even though it's finite, it's pretty big. And here's a graph. I think this was also shown on a cover slide. This is just a graphical representation of what I gave you on the table. So these are the known ABC triples, just how many are known with given qualities. Or the frequency. This is a relative frequency. So as you can see, there's a lot known with small values of Q, and there's many fewer known with larger values of Q. By the time Q is 1.4, the fraction is minuscule compared to how many there are known for around 1 to 1.05. So the frequency does drop off quite a bit as Q gets large. And I guess I just want to finish by showing you what the current records for the ABC triples that are known with the highest quality. It turns out the highest known quality is 1.6299. This was discovered by Eric Reisel. I don't have the years, unfortunately, but I think this was discovered fairly recently, maybe the last 20 or 30 years. And yeah, and they also give you the values of A, B, and C factored out. It turns out that for the highest known quality ABC triple, A is 2, B is, 3 to the 10th times 109, and C is 23 to the 5th. Usually these prime factors are pretty small. The exponents can get big, especially for the ones with high quality, but anyway. Just a list of the top 5, and So there are some triples with very high known values of Q, but not that many. Anyway, that concludes my talk today on ABC conjecture. Thank you for watching. Long live math, and I'll see you guys next time. Bye.